Hello, everyone. I'm happy to present this topic, streaming Lakehouse with Kafka, Flink and Iceberg. A quick introduction about me. I'm Zabeer Farook. I work as a technical architect in Crédit Agricole CIB in Singapore. I am passionate about stream data processing and event-driven architecture. I also love traveling and exploring places. You can follow me in LinkedIn by scanning this QR code, what you see here, and I would be glad to connect with you all. Now, coming to the agenda for this talk, so I'll be discussing some of the challenges with data warehouse and data lake. And then I will introduce you to Lakehouse, what is a Lakehouse, and how we can potentially address some of these challenges posed by data warehouse and data lake. And then I'll discuss about what is a streaming Lakehouse, what kind of elements you need in a Lakehouse to make it a streaming Lakehouse. And then I will also spend some time diving into Apache Iceberg, which is at the center of standard Lakehouse. I'll also spend some time, very high level overview about Kafka and Flink. And finally, I also have a demo. I don't think I'll be able to do a full-fledged live demo as such, but I would try to give a outline of the demo and followed by Q&A. All right. So challenges with respect to data warehouse. Data warehouse has been there for a long time now, right? From the 80s, it is there. On one side, we have legacy data warehouse, and on the other side, we have the modern cloud data warehouses. So with respect to the legacy data warehouse, the issue is that the compute and storage are always coupled, and you cannot scale one of them independent of the other. And also, the cost is always high with respect to a legacy data warehouse. When it comes to this modern cloud data warehouses like your Redshift, BigQuery, Snowflake, it's much versatile and flexible. But at the same time, they use proprietary architecture. It will use proprietary table formats, proprietary file formats, and so on. So it means we are dealing with a very closed architecture. It means we have to deal with vendor lock-in, and as well as the data is also logged in into those platforms. And needless to say, the cost remains very high with cloud data warehouses. Now we will discuss some challenges with respect to data lake. So data lake is something which leverages, it's much flexible compared to a data warehouse, and it leverages the cheaper storage, object storage, as well as you can also bring in multiple engines, right? Engines to work with, like Apache Spark, Apache Flink, and so on. So it gives this freedom of using any of your object storage engines, and also the compute engines, right? You can choose from. But what is lacking here is there is no unified or a strong metadata layer. So what it means, you cannot have transactional guarantees, right? You cannot have atomicity, consistency, isolation, durability, which was the case with data warehouse. Data warehouse provides you transactional guarantees, so you are losing it actually with in data lake. And also, we face a lot of data governance issues, and often we have to deal with a scenario called data swamp, where at some point it will be very difficult to find your own data. It will become as if you are searching a needle in a haystack. So that's some of the challenges about data lake. Now, I will also talk about some hybrid data platforms. So enterprises today have more than one data platform, also more than one hyperscalers in their disposal. So it could be to do with historical architecture decisions. It could be due to some of the mergers and acquisition which they have gone through. So the problem here is the data lives in silos, right, in different data platforms, and without interoperability. So you cannot easily query data from one data platform to another. So often we may have to copy the data from one data platform to the another, which means we are actually duplicating the data, right? Having multiple copies, and even these copies, you cannot guarantee data is consistent, right? You will have to deal with data synchronization issues, and overall, all these factors will again drive up the cost very high. So it becomes a very expensive solution. Yeah, now let me introduce you to Lakehouse. So Lakehouse is something which came around 2020. It was made popular by Databricks, the term itself. So basically, the data lakehouse combines the best of both worlds, from the data lake as well as the data warehouse, right? So it combines the best features from both of these platforms or both of these architectures. So the key differentiating factor in a lakehouse is the presence of the metadata layer, so which gives the very much needed data governance and indexing and data management capabilities. And typically this metadata layer is something which can be fulfilled by what we call open table format, right? So we have multiple open table format out there. You could use Apache Iceberg as one of the choice. You could also go for Apache Hudi. It could be Delta Lake, or it could be Apache Pymon. At least there are four available options for this metadata layer. And similar to data lake, even in Lakehouse, we are going to leverage the object storage. So it means your AWS S3, Google Cloud Storage, Azure data lake storage, or something similar, which is S3 compatible, right? We could use that. And here also, you could bring in multiple different compute engines based on your need. You could use Apache Spark, you could use Apache Flink, you could use Dremio. Like you have several Trino, like many compute engines and query engines you can play with, all right, in a lakehouse. And basically it provides an open architecture, right? It presents you an open architecture where we can choose the different components of this lakehouse, and there is no rigid choice you have to make, right? You have more flexibility here. And of course the cost efficiency also you are going to get. And basically the lakehouse combines the reliability, performance and transactional guarantees of your data warehouse, along with the cost efficiency and scalability of the data lake. So all these good features from these two architectures are ticked in a lakehouse, right? And more so, it also provides interoperability, which is very very key, right? So that you can easily exchange data between different platforms with respect to this open table formats. And also there is no lock-in, no vendor lock-in, no data lock-in, right? So we are almost solving all these challenges we discussed before. Okay, so far so good, right? We talked about Lakehouse. What about real-time data? So real-time data processing is very, very critical, especially in this current fast-paced environment, right? Where we have to make faster and time-critical decisions, especially if you're dealing with fields like compliance, uh, like real-time payment processing, fraud detection, let's say predictive maintenance, right? So all these fields need real-time decision making or near real-time decision making, and your normal batch analytics is not going to help much. So, and your data also needs freshness, right? Data needs to be fresh so that you can make faster and informed decisions. So with that, yeah, we will talk about what we call is a streaming lakehouse. So if you see the difference between a lakehouse and streaming lakehouse is nothing but you have capability to perform streaming ingestion to your lakehouse. So it means you are able to receive data from sources like Kafka, real-time sources like Kafka, which you can ingest into your lakehouse, plus the presence of some stream processing capabilities, real-time stream processing capabilities with engines like Spark streaming or Flink streaming, right? So you are able to process this raw data which you are streaming and perform some kind of aggregation and standardization at real time. And also you have real-time analytics capabilities, which can really help with making real-time informed decisions. One of the other use case here with the real-time stream processing is with you can also achieve real-time machine learning, which is very very critical in this current AI environment. So now we'll spend a little more time. We will spend some more time in detail, like have a detailed look at this streaming lakehouse. So on the leftmost side, what you have is data sources. So your data sources could be structured data, semi-structured data, or unstructured data, and it could be your operational database, or it could be some IoT devices emitting some events, or it could also be some logs coming out of your applications, or some social media feeds and so on, right? So this could be your data sources. And at the ingestion layer, you could perform a streaming ingestion, or you could perform a batch ingestion, right? Depending on the data source and depending on your need, right? So when I say streaming lakehouse, it means it has both batching and streaming capabilities. And again, depending on the need, you could use Apache Flink, you could use Apache Spark, Kafka streaming, or even you can use some new plays like Rising Wave, or even a lot of other options we have to stream the data. And when it comes to storage and processing, uh, as we already discussed, you can leverage object storage. So you could use MinIO, you can use Google Cloud Storage, Amazon S3, or Azure Data Lake Storage, right? There are multiple options to choose from. And the data files itself will be stored normally in Parquet format, but there is also a possibility to store it in Avro or ORC format. And the key factor which we discussed, which distinguishes a data lake from a lakehouse, is the presence of a metadata layer. And again, metadata layer is something which can be fulfilled by Apache Hudi, Delta Lake, Apache Iceberg, or Apache Poimon, right? There are several options. And this metadata layer is the one which brings in data governance and SQL query capabilities to a lakehouse. There is also another element here. If you see catalog, so catalog is something which is a service which keeps track of the latest metadata files for a given table. So whenever a query engine or a compute engine needs to work with a lakehouse, it needs to use a catalog, and the catalog is the one which will provide it with the latest metadata files through which it can discover the actual data files down here. So that's the catalog. And even for catalog, we have multiple choices. You could use a REST catalog from Tabular. You could also use Polaris catalog. You have Nessie. You can also use AWS Glue catalog. There is also Databricks Unity catalog and so on, right? There are multiple catalogs out there, right? You can choose that. And when you ingest the data, you could have ingested the data in a raw format, right? If you are following a ELT kind of approach, or you can do a ETL approach where you already cleanse and transform the data before you load it into your lakehouse. So depending on that approach, you may want to still employ a processing engine, either in batch mode or streaming mode. So again, you can use Apache Spark, Apache Flink, Dremio, or even like the other variety of compute engines out there to perform some cleaning, transformation, and aggregation of your data. And you can also organize your data in Lakehouse in different layers, like a bronze layer, a silver layer, or a gold layer, depending on whether it's a raw data or a transformed and cleansed data or an aggregated data, right? And next up, we have serving layer. Serving layer is basically which exposes these data from the Lakehouse in terms of APIs and in terms of SQL capabilities to the consumption layer, right? Now, consumption layer is your reporting BI tools, your data science and ML tools, your visualization tools, and so on, right? These are your consumption layer, which needs the data. And it can use the query engines like Trino or Spark SQL Thrift Server or Star Rocks, or even there are multiple other choices which exposes this data from the lakehouse to this consumption layer. So this is how typically streaming lakehouse looks like when we talk about all the different elements, different layers, and different components which makes a streaming lakehouse. Now let's spend some time understanding Apache Iceberg itself. So Apache Iceberg is a high-performance open table format, purpose-built for large-scale analytics. Basically, it brings the simplicity of SQL to the big data world, right? Where you are able to perform SQL queries on your cloud object storage, right? Which was not possible otherwise, with transactional guarantees, right? You could also perform updates and deletes, and you can also expect ACID guarantees out from that. And what's the role of Iceberg in a lakehouse? So Iceberg is one of the several options which can be used as a metadata layer in a lakehouse architecture. So when it comes to the specification or the architecture of Iceberg itself, like it proposes to have a catalog, which is Iceberg catalog. So as I already mentioned, Iceberg catalog is the one which keeps track of the current metadata pointer. Okay, so as you know, there is a lot of metadata files. So this Iceberg catalog's responsibility is to keep track of the latest metadata file per table, right? For each of the table in the Iceberg, it needs to keep track of the latest metadata pointer. And any of the compute engines or query engines which needs to work with Iceberg, either to read data or to write data, it has to connect through this catalog, which will provide it with this metadata pointer, and through which it can navigate all the way to the data files. Now, the metadata layer itself is consisting of a bunch of files, metadata files. So the first one here is the metadata file itself. It's called metadata file. It's normally in a JSON format, which normally contains the table schema or partition or table schema, partition schema, and also a list of snapshots. Okay. And each of these snapshots represents the state of the data at that point in time, meaning whenever you update data to Iceberg, right, it will create a snapshot to represent the state of the data at that point in time, right? So why this is needed? Because it provides something called time travel capabilities, and for that it takes a snapshot with each of the write whatever you do with Iceberg. So metadata file also contains one or more snapshots, and each snapshot will further point to manifest list file. And manifest list file basically contains some stats about the table, and which in turn points to one or more manifest files. And the manifest files contains the metadata about data files and also the location of the data file. So this is how it is organized, the metadata layer. And at the end, what you have is the data layer. These are the actual data files, which are typically in Parquet format. But it's also possible to have these files in ORC or Avro format. Now let's move on. Hope it's clear here. Now let's talk about some of the features and benefits when it comes to Apache Iceberg. So Apache Iceberg provides expressive SQL, as we have seen before. It follows an open specification, so it means it provides basically a specification which the different compute engines can implement it based on that specification. And the key features are schema evolution and partition evolution, where the schema and partition can be changed without really affecting or without rewriting the existing data, right? Halfway through, if you decide to change the schema or change the partition, the existing data need not have to be rewritten. So that's the best thing about Apache Iceberg. And time travel and rollback are other key features. So using time travel, you can query a data based on a past date, right? So you can check, okay, as of Jan 1st, how is the data looking like, right? So you should be able to perform such queries. And it's ACID compliant. And there is also features like branching, merging, and tagging, data compaction, as well as hidden partitioning. When it comes to the benefits, I would say it truly presents an open architecture. It avoids the vendor lock-in and data lock-in challenges, which we discussed before, because you can use different compute engines, right? You have multiple choices. Not only these choices, whatever you see here, there are more than this. And you can also use different storage, right? It's not okay, you can only use S3, AWS S3. You can use different Google Cloud Storage, Azure Data Lake Storage, and so on, right? So it truly presents open architecture and avoids vendor and data lock-in. Okay, this is something very interesting. So if you followed the data world closely last year, right, even with all the buzz about Gen AI and stuff, Apache Iceberg was making a lot of noise, right, in the data world. So it all started with Snowflake, which open sourced a catalog called Polaris, which is an Iceberg catalog. And around the same time, Databricks acquired a company called Tabular, which was originally founded by the creators of Iceberg. And Databricks acquired this company, and then the annual revenue rate for Tabular was around 1 million at that time, $1 million. But Databricks paid a staggering, I mean, we don't know the exact figure, but anything between $1 billion to $2 billion to do this acquisition. So it made a lot of news then, right? And even all the other major cloud providers and data platform providers also extended support for Iceberg. For example, Confluent announced a product called Tableflow, using which a Kafka topic can be materialized to a Iceberg table with the click of a button. And even AWS S3 announced managed Iceberg tables back in December 2024. And even just a few days back, Cloudflare has announced a catalog called R2 Data Catalog. So Cloudflare also provides object storage, cloud object storage, and they have announced something called R2 Data Catalog just recently. The best thing about that is they're not going to charge egress on the Iceberg queries whenever you do the data from R2 storage, right, which is phenomenal. Now, who is the winner after all this battle? Obviously, without doubt, it is Iceberg, because the adoption of Iceberg is continue to increase, and it is becoming kind of a key standard when it comes to open table format with Lakehouse. So Kafka and Flink in the Lakehouse, right? So I'm not going to spend a lot of time discussing about Kafka and Flink. So briefly, Kafka is a distributed PubSub and event streaming platform. It can handle a huge volume of messages with low latency and high throughput, also with fault tolerance. On the other hand, Flink is a unified stream and batch processing engine. It can handle a large-scale stateful stream processing with low latency and high throughput. Kafka and Flink together can transform a lakehouse into a streaming lakehouse, right? So we are not saying, okay, these are the only choices, but these are some key choices you can make to transform a normal lakehouse with streaming capabilities, thereby calling it a streaming lakehouse. Now we are almost at the end of the presentation, and let me do a quick recap. So data lakehouse offers a cost-effective alternative to data warehouse, and it avoids vendor and data lock-in. It is powered with open table formats like Iceberg, and Iceberg intent has features like schema evolution, partition evolution, time travel, which can keep the operational and maintenance cost low. A streaming lakehouse is something which offers streaming ingestion and processing capabilities to power real-time analytics and decision making. Kafka and Flink offers real-time capabilities to a lakehouse, along with like even other tools which you could use. And Trino and other distributed core engines could be used to really help integrate the lakehouse with your consumption layer, which is nothing but the BI, analytics, ML, and data science tools. Now we talked all good about Lakehouse. Yes, it is indeed powerful, but it's not a magic wand, right? So it's not a silver bullet. So you still need to take care of data quality by implementing data validation checks. You need to take care of security and compliance by leveraging the security offered by your storage layer solutions. You could tap onto some of the catalogs which offers RBAC policies so that you can have finer control of your Iceberg tables. And maintenance of Iceberg tables is also very, very important, especially in a streaming context. You can have a lot of small files generated from streaming, and you may want to perform compaction of these small files into optimal size files using the compaction offered by Iceberg. And you could also put some snapshot expiration so that you don't create a lot of snapshots and keep it forever. So you can do some periodic pruning and expiring of the snapshots to keep the performance in check. So yeah, with that, I've come to the demo. As I mentioned, I may not have the full time to do a full-fledged demo here, but I would like to do a quick outline of the demo. So that the intention of the demo is to really show some hypothetical use case of a streaming lakehouse with things like Iceberg, Kafka, and Flink. So that like you can relate to the talk and try it yourself also. Like you can scan this QR code, what you see here, which will take you to the GitHub repo where this demo code exists. So you should be able to check it out and try it yourself, and there is clear guidelines on the different steps, so you should be able to relate to this talk. But let me provide a quick outline of this demo. So here we are using Kafka Connect with a data gen connector. So this data gen connector simulates page click events. So each page click event will have a page ID, a user ID, as well as a timestamp. So with the Kafka Connect, we are streaming this event to Kafka. And we also use, there are two other data files, like user data file and page data files. So essentially, this is mapping the user ID to some information about the user, like which region the user belongs to, like Asia or Europe, like that. And page data file maps the page ID, whatever we ingest here, to details of the page, like the page description, right? So what we are doing is we use Flink to stream these raw data. So one is this page click event from Kafka, and these two file data from the file system. We are ingesting this data into Iceberg, right? And we also perform a join between these three data sets because we have common IDs between them. And this enriched stream also we are ingesting into Iceberg. Our Iceberg setup itself is made of MinIO, like we are using MinIO as a storage. And we are using tabular S catalog as the Iceberg catalog, which needs to be there for Flink to work with Iceberg. And even for Trino, we are using Trino as the query engine. So even for Trino, it needs the tabular S catalog to perform any queries on Iceberg. So for visualization, we are using Apache Superset. So the key idea like here is to perform some real-time analytics using some, let's say, some pie charts to really identify some insights from these page click events in terms of, who are the users, or like which region these users come from who are frequently using this website. And in terms of pages, like which pages are more often visited, right? So these kind of analytics, we can do it by creating some pie charts, and the queries for analyzing that can come from Trino. We can integrate Trino and Trino queries Iceberg. So this is a typical quick outline I wanted to give here. And you should be able to follow the demo by scanning this QR code. I wanted to end this talk by saying the future belongs to open data architecture. So what REST did for the web some time back, like right, which is being done by Apache Iceberg for the data architecture side, right? It is essentially creating open interoperable standards, right? So this is what I wanted to quote and end my talk. And maybe I will also quickly show the GitHub repo. Like this is the repo. So if you scan the QR code, you will find this. So already we have given all the instructions here so that you can follow it well. Okay. So you will also, like if you try it yourself, it's a Docker Compose based setup. So finally, you will be able to create some cool dashboards like this to really check, your users, what are the top regions the users come from, like what are your popular pages your users are visiting, right? So this is a simple demo, but just to really reinforce the concepts or whatever we talked about in this talk by really trying it out yourself. It's a Docker Compose based setup. All right, so that's it. Thanks for tuning in and thanks for listening to this talk.